Okay, so we're going to talk about Chapter 2, Part 1, which is power and radical functions. Power and radical functions. So, as is usually the case, I'm going to try to always warn you guys when we encounter a problem that's often missed on the test. So here's a definition problem that's often missed on the test. Being able to identify a power function. So a power function looks like this. It's any function of the form y equals a times x to the n power, where a and n are non-zero reals. So a and n can't be zero, and they can't be non-zero numbers. So it's any function in that form or that could be modified to be in that form. So algebraic manipulation, if it can get you to this point, then it's a power function. So any function of this form, y equals a times x to the n. And again, often missed on the test for whatever reason. Monomial function is any power function or constant. In other words, y equals a times x to the n, or y equals k, where k is some constant value. Radical function is any function that has a variable under a root. So any function with a variable under a root. So when I have radical functions, the possibility for what's called an extraneous solution exists. And you've probably heard me mention this already a time or two. But it's when legitimate algebraic steps arrive you at a solution that is false. So the possibility exists when you're solving radical equations. So this is a false solution. So you must check your answers. In other words, plug them back in when solving radical equations. And there's a quiz question where one of your answers is going to be extraneous. And it's multiple choice. So I'm going to put the extraneous solution in there as a potential solution. Even telling you that, I bet some of you still get it wrong. Okay, any questions about any of these definitions? Thoughts or comments? All right. So monomial functions have four different flavors, if you will. So if they are of the type f of x equals a times x to the n, the behaviors of the function are largely determined by that a and n. So n's evenness or oddness affects the way the function behaves, and a's positivity or negativity affects the way the function behaves. So all you need to know from this page are these general shapes. When n is even and a is positive, it will have this general shape, the same n behavior. This stuff in the middle can be a little different, but it will, in general, look like this. When n is even and a is negative, you'll have this kind of shape. Now, notice that in both cases, when n is even, the n behavior is in the same direction for both infinity and negative infinity. So that's an important observation to make. And all this other stuff, it's implicit in the graph. In other words, it's built into it. But it is in your book, and you can consult it at any time. Let me shrink this down a little bit where we can see the whole thing. Yeah, there we go. So if n is odd, notice that the n behavior is towards different directions. If A is positive, it's like this. If A is negative, it's like that. So n even, which means it goes in the same direction. N odd, it goes in different directions. And positive and negative just cause it to switch over the x-axis, flip over the x-axis. So those are the four basic behaviors of monomial functions. At least where the characteristics you see are concerned. The zeros and all that can vary wildly. So no mention of zeros here, but the n behaviors, the symmetry, minimums, maximums, etc., those are all predictable based on those characteristics. All right, anybody need extra time? Okay, you guys are speedy little writers. Okay, so this is our first monomial function we're going to describe. I see that A is positive, 1/2 is greater than 0, and 6 is even. So the function f of x equals 1/2 x to the 6th power. So I have A greater than 0, and n is even. So A is greater than 0, n is even. That means it's going to be like this upper left. It's going to look something like that. So we'll graph it on the calculator and see how closely it conforms to that predicted shape. So 1/2 times x to the 6th power. You see, it's a skinny little parabola that gets real flat at the bottom. Doesn't go below the x-axis. So there we go, something like that. So let's describe the domain, range, intercepts, end behavior, continuity, and all that stuff, just based on our sketch of the graph. So first of all, the domain, as is the case with all monomials and all polynomials for that matter, the domain is x is a real number. In other words, there are no constraints on the domain. That's why polynomials have the definitions they do. Polynomials don't allow division by variable. They don't allow variable under a root, and they don't allow variables with negative exponents. All those three things are specifically to prevent domain breaks. So x is a real number, is our domain. Any real number. Range. In this case, it's going to be y greater than or equal to 0. Because I can see the lowest point here is at 0, and it's included. So if I trace, I see the origin is a point on this function. And if I go to the right, well, I'm going up. Go to the left, it's also going up above 0. So 0 is the lowest point. Intercepts. So as we just discovered, the origin is an intercept for both the x and the y-axis. End behavior. You know, we like to describe that with limits in pre-calculus because we want to get you guys accustomed to using more sophisticated mathematical symbology. So the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x is going to be infinity in both cases, positive infinity. And then the continuity and intervals of increasing and decreasing behavior. So continuity. So just look at this and tell me, can you graph this without picking your pencil up? Yeah, there's never going to be a break. So this is what we call a continuous function. And then intervals, it's got two, negative infinity to 0, on which it is decreasing, and 0 to infinity, on which it is increasing. So there are all the characteristics of that function based on that sketch of the graph. Stop me if you have a question. All right, everybody cool? Move on to another one here. So here we've got negative x to the fifth. So in this case, a is less than 0 and n is odd. So this is going to be like that bottom right type of graph. And if I sketch it, and we'll punch it in the calculator, but it's going to look something like this. A little flatter around the origin, but it's not going to impact any of our analysis here. The domain, again, as is the case with all polynomials, including monomials, it is all real numbers. The range, in this case, also all real numbers. Do you see why? Compared to the last problem? That's a very important distinction to be able to make. To look at that last graph and understand the graph had a constrained range, but this graph has all real numbers as its range. Intercepts, once again, it includes the origin. So both of those are going to occur at the origin. And then continuity, or I'm sorry, end behaviors next. So that's the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. So to the right, you see how it goes down, down, down forever? And so that's negative infinity. And to the left, it goes up, up, up forever. So that's positive infinity. So be careful with that. That's part of those characteristics that were listed. So I could have known this just by this. Didn't even need to sketch the graph. Continuity, and then intervals of behavior. So again, the case with all polynomials, it's continuous. The definition of a polynomial forces this to be true. And then intervals, just got one interval, and it's decreasing everywhere. Okay, any questions about that one? All right, here's one for you guys. So, sketch this graph, tell me where it's increasing or decreasing. If you're not sure where to begin, I'll come help. Man, boy, Roddy using Desmos over here. Hey, boys. In the future. All right, Holden, if you will, tell me the first interval and its behavior on that interval.
That is x approaches infinity f of x equals mean.
So that's the end behavior. Here we're concerned about the intervals of behavior.
I'm sorry. From negative infinity to 0, it's decreasing.
Good.
And from 0 to infinity, it's increasing.
Good. All right, so you guys should have been able to look at that graph and know this right away. One of the characteristics you should be able to infer from a sketch of a graph. Example 2. What if they have negative exponents? We'll make them. A negative n creates a different set of behaviors, and it's no longer going to be a monomial. So we can't just say the domain is all real numbers, for example, because the behaviors now will be different, and you'll have some discontinuities, you'll have some other things pop up. So 2 times x to the negative 4. So in this situation, we're going to have to use our calculator to give us a good sketch. Because again, these are harder to predict than the ones that are actual monomials. 2 times x to the negative 4 power. Okay, so the sketch is going to look something like this. Pretty funky behavior. It's got a discontinuity at x equals 0. It's an infinite type. But let's talk about the domain. So the domain is going to be x is not equal to 0. Because remember that another way to say a negative exponent is a positive exponent in the denominator. So I can write that like so. And you see that we have a division by 0 at 0. So that's why this is the case. All right, the range. So no matter what I plug in for x, this will never quite be 0. I can get arbitrarily close to 0. And this is really the distinction between a calculus-minded mathematician and a conventionally algebraic-minded mathematician. Can you think in terms of getting closer and closer and closer to a thing, but it being impossible to actually get there? That's the essential idea in calculus. But anyway, we'll get closer and closer and closer to the x-axis, never quite get there, meaning y is greater than 0, not greater than or equal to, because we could never quite get there. Intercepts. There are none. It cannot touch either axis ever as a consequence of x equals 0 being discontinuity and y equals 0 being a value that this expression could never get to. In behaviors, it's a little more interesting this time. So the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x. In both cases, ladies and gentlemen, will be 0. It gets closer and closer and closer to 0, never quite getting there. All right. Next is continuity. So look at this. Can I graph this without picking my pencil up? No, it is discontinuous. So it has a infinite type discontinuity, which I'll abbreviate here, at x equals 0. And then intervals of behavior. So it's got 2 intervals from negative infinity to 0 and from 0 to infinity. And you'll see it's increasing on the left interval and decreasing on the right interval. Questions about this, sir?
So if we do end up having a negative, will they always like kind of have that exact same shape like the other ones, or will it differ depending on?
Okay, so the question was, with a negative exponent, can we expect this shape to be typical?
Yeah.
Yes, if it's a negative even number.
Okay.
If it's a negative odd number, it would go to positive infinity on one side and negative infinity on the other. Think about you remember what the negative x to the 5th we graphed looked like? how the end behavior was in two different directions. So think about it kind of like that, but flipped inside out, where the end behavior now goes around the discontinuity. So yes, if it's even, no if it's odd. Good question, Kyle. Other questions? All right. So let's go back to full size here. 2 times x to the negative 3. Now, once again, a little bit of a difference here. We've got a negative exponent, and n is an odd number in addition to being negative. So as we predicted a second ago, that's going to look a little differently on the graph. So 2 times x to the negative 3 power. So we have this behavior now. So our domain, once again, I could rewrite this as 2 over x to the 3rd power. So you see that 0 does create division by 0. So we once again have this domain. Our range, y could not be 0. Every other value is defined. For the same reason as the previous problem. Intercepts. Once again, none. End behavior. Same as last time. The limit as x goes to infinity of f of x is 0. And the limit as x goes to negative infinity of f of x equals 0. Continuity. We have an infinite type discontinuity once again at x equals 0. And then intervals of behavior, once again there are 2, and they are from negative infinity to 0 and 0 to infinity. And in this case, we are decreasing on both of them. So stop me if you have a question. Thought, comment? All right, cool. Let's move on. So here's one for you. Describe the end behavior of the graph 3 times x to the negative 5th power. Let me make that a little larger. So 3 times x to the negative 5th power. Tell me what its end behavior is. The limit as x goes to infinity and the limit as x goes to negative infinity of f of x. If you're not sure how to begin, raise your hand, I'll come help you. That's quick. Incorrect.
I haven't written it down.
Sure. So the graph is going to be our best source of information. So we'll punch in this case 3 times x to the negative 5 power. And we see this shape, very much like the previous problem. But do you see what happens as x is getting big in both directions? Getting closer and closer to 100. Right. That's it. Okay. Rowdy, tell me what these are going to be equal to.
0.
Yeah, both cases. 0 is what the graph is approaching. So again, graphical analysis is the name of the game here early in the book. That graph is your best source of information. You could plug in some really high x values, but that's tedious. And I'm a super visual guy. So for me, the graph is the thing. If you're more algebraically oriented, you may want to just plug in really high positive and negative x values and see what happens. You're going to get closer and closer to 0. But interpreting the graph is the most efficient way to solve these sort of problems. Okay, so rational exponents. First of all, I want to tell you that rational exponents and radical functions are the same thing. And I want to teach you why first. So if I have a rational exponent, what's the root word of rational?
Ratio.
Which means to compare by what operation? Indeed, so we're comparing things by division. Rational exponents look like this. X to the m over n. So some fractional exponent that is compared by division or rational. So I could rewrite this in either direction as the nth root of x to the m power. These are equivalent statements. So for example, if I had x to the 4/5, that is the same thing as the 5th root of x to the 4th power. So these are interchangeable ways to describe this expression. No difference. So this is a rational expression, or rational exponent rather. And this is a radical expression. So those are interchangeable ways to describe these relationships. Okay, so here we go. X to the 5/4. We know by that argument I just made, this is the 4th root of x to the 5th power. So describe all of those characteristics we've been describing, but we're going to do it using the graph as a guide. It's going to look a whole lot like y equals x, at least in quadrant 1. X to the 5 divided by 4. And it's important to put this in parentheses. Some calculators, you can get away with not doing it, but this is not such a calculator. So here we see, starting at the origin, and then going upward into quadrant 1, we've got this slightly inflected graph, so it's not exactly diagonal. So looking at that, the domain is going to be x greater than or equal to 0. The range is going to be y greater than or equal to 0. The intercepts are going to both occur at the origin again. The end behavior. Well, first of all, the limit as x goes to infinity of f of x is infinity. But the limit as x goes to negative infinity of f of x. So here's a little calculus lingo for you. When it's outside of the domain, we write DNE. That means it does not exist. So that limit does not exist. Makes no sense to even talk about it because you see that's an undefined part of the domain. Continuity. So you may say discontinuous, but starting here, can I graph it without ever picking my pencil up? Yes. So this function is continuous on its domain. So we would say continue. And then intervals of behavior. So it's got one interval from 0 to infinity on which it is always increasing. Graphical analysis. Stop if you have a question, thought, comment. Everybody feeling good after your 5-day break? So we're doing this next week for sure. Most teachers speculate this schedule will persist through the rest of the semester, but no way to know for sure about that. But I discussed it with another teacher, and he made some pretty good arguments as to why we would probably be on this for the rest of the semester. So I tend to think that's likely. So you're going to be stuck watching those videos on Monday and Tuesday. Let me know if those are deficient in some way. All right. So example 3 here. Graph at part B. Graph and analyze the following. So this is 4x to the negative 2/5. So I have a negative rational exponent. So if I were to rewrite this, that's 4 times the 5th root of x to the negative 2 power. See how funky that expression is. So let's just graph it and kind of see. There's almost too much to keep up with there to do a good mental graph. So 4 times x to the negative 2 divided by 5 power. I'm not 100% sure. Yeah, that should be. Yeah, 0 is undefined. Let me check one thing real quick. Let's go to a really big x value and see if it's, yeah, slowly, ever so slowly approaching 0. Okay. So kind of like that. Domain. X can't be 0. Range. Y greater than 0. Intercepts. None. End behavior. In both cases. Towards infinity and negative infinity of f of x. Once again, we're approaching 0. Continuity. It is discontinuous. It has an infinite discontinuity at x equals 0. And intervals of behavior, there are 2. Negative infinity to 0. On which it is increasing, and 0 to infinity on which it is decreasing. So any questions about anything we've done so far? Done a lot of dang graphical analysis so far. We're just graphing like mad people up here. Okay. So here's one for you. Tell me if this function is continuous. 4 times x to the 2/3. Can you graph it without picking your pencil up? If you're not sure how to begin, raise your hand. I'll come help you. Okay, Ian, what do you think? Let's take a look at the graph. So 4 times x to the 2/3 power. So if I trace here at 0, you see it does exist. I go off to the left. So that's a pretty exotic situation, and I doubt you've ever seen that, Ian. But even though it has what's called a cusp, which is a sharp point, very unusual, and not differentiable, but you don't have to worry about that. It is continuous. So this is a continuous function. But this sharp point is really unusual behavior, and it does cause it to have some problems with other mathematical operations. But as far as continuity goes, it is continuous. And the reason why is I could graph it without picking my pencil up. So that was a tricky graph to analyze. You had to actually test the origin to see. Another way you might have known is to just plug 0 into that and see what happens. 0 squared is 0, third root is 0, 0, 4 times 0 is 0, so it does exist. But a tricky graph to analyze. Okay, so power regression. We're going to use a power function to model real data. So this is a tricky calculator-based problem. You must have your calculator out for this, or your emulator or whatever. So the first task is going to be to put our data in. So if I hit the Stat button, then the Edit button, I want to edit L1 first. So I'm going to go up to the heading, and I'm going to hit Clear, not Delete. Don't hit Delete. I have to reset your calculator. Hit Clear, then the down arrow. That clears all that data. Then go over to L2, Clear, down arrow. I'm going to come over here because I can put the data in much more quickly with the keyboard. So we're just going to put in the L's, which is the length of the golden cat, African golden cat. If you wonder what that creature looks like, it's pretty cool. I'll show you. Like a really big, ferocious house cat. I would like to have this to protect my home against invaders. But this is the length in centimeters and the mass. So you're talking about a creature 2.5 feet, something like this. And then 11 kilograms of mass is about 25 pounds. So roughly 4 or 5 times the size of an average house cat. All right, so let's put this in our calculator. First of all, the lengths are going to go into L1. So 72, 72, 73, 74, 75, 76, 78, 79, 80, 83, 84, 85, 86, 88, 89, and 90. Now we'll go over to L2 and we're going to put in the masses. 11, 12, 13, 15, 15, 14, 15, 15, 14, 16, 16, 15, 17, 17, 18, 18. And notice that the same number of values exists in both lists. That has to be the case or this won't work. So if you have one too many in either list, you've screwed up and left one off somewhere. So start over. All right, once you've done this, we're going to quit to the home screen. We're going to hit Stat. Go over to the Calculate tab, and we're going to navigate down, down, down until we see PWRREG, Power Regression. If we hit Enter and Enter, that gives us this power function to model this data. Let's see just how good it is, shall we? So go to Y equals and clear out whatever's there. Go up to plot 1 and hit Enter. That turns it on. So this is going to show us the data we just put in. Let's choose our window carefully. Notice these links are between 70 and 100. So let's just go 0 to 100 for the X values. And then for the Y values, this is the mass. Let's go 0 to 25. That'll cover it all. So there's our data clustered around here. Let's see how good our regression model is for that data. So this is a tricky process, but it's worth learning. If you go to VARS and then statistics and then equations, you see REGEQ. What this does is calls the last regression equation found. So whichever one you just found with your calculator is what it will show. If you don't do the first step, this will not work. So I've seen people that watch their neighbors find the regression equation and then try to call it on their calculator. No, it doesn't work that way. You got to do it on yours as well. So if you have called the regression equation, this will punch it in here and save you all that typing. And we graph. All right. Does that appear to model the data pretty well?
Yeah.
About as perfectly as you could with the power function. So what we would write is, let's round to the nearest thousandths. So 0.18 times x to the 1.54 power. Oops. So that's about our best model we could produce with the sophisticated software of the TI calculator. Written roughly, I don't know, 20 years before you were born. Okay, so this is a different plot. Notice I use different x's and y's. That's why it looks a little different. So here the task is it's basically the same problem. We're going to use the data to predict the mass of a golden cat that has a length of 77. Notice that's not on the table here. So you get a cat that is 77 centimeters in length. What would you expect its body weight to be based on our model? So if we go to our graph and we hit the trace button, notice it defaults to plot 1. We don't want plot 1. We want, if I hit the down arrow, we want y sub 1. That's where we put our regression equation in. So navigate to that, then type in 77. And I see that I should expect it to be about 14.08 kilograms. About 14.08 kgs. They use the metric system in most places. The United States is basically the last bastion of the imperial system. Inches, feet, pounds, etc. Everybody thinks this is the last generation. We're going to go to the metric system, and then we never do. So I'm not sure it'll actually ever happen. United States citizens are creatures of habit, and you know, we like to have our unique identity from those European people. Okay, so we'll skip this one. Radical functions. So you have f of x equals the nth root of x, where n is a positive integer, is the simplest type of radical function. And if n is even, you're going to begin at the origin. If n is odd, you're going to be defined for all x's. So an even index like a square root, you can't have a negative input. An odd index, negatives are okay. And so you have that behavior. This again is in your book, but what I would be concerned about is just this bit.
Robert, Isabella Morris to the office for just.
Okay, so let's graph one of these. I've got 5 times the square root of 2x cubed, and we're going to describe its behavior based on a sketch of the graph. So if I go to y equals, clear out whatever's there, and turn the plot off. We don't need those goofy points on our graph going forward. So 5 times the square root of 2x cubed Windows weird. I need to hit zoom in 6. There we go. All right. So the graph is, and if I trace here at the origin, I see it is defined there. So that's included. So the domain is going to be x is greater than or equal to 0. The range is going to be y greater than or equal to 0. The intercepts are going to both occur at the origin. X equals 0 is the x-intercept, y equals 0 is the y-intercept. In behavior, so I got the limit as x goes to infinity of f of x equals infinity, and the limit as x goes to negative infinity of f of x does not exist. Continuity. So remember that if we can graph it without lifting our pencil up, which is the case here, it is continuous. So its domain is not all real numbers, but it is continuous on that domain. And intervals of behavior, just one. So from 0 to infinity, we're increasing here. Stop me if you have a question, thought, comment. What do you think about chapter 2? Easier so far?
Mm-hmm.
Most people find that to be the case. Chapter 1 is very general. In other words, it covers a lot of stuff. Going forward, the chapters will be more specific. So the material might be a little harder, but it's less of a general approach to that material. Okay. So tell me what the intercepts are for the graph f of x equals negative cube root of 8x squared minus 4. That's a fairly complicated expression. Let's see if you can tell me what the x and y intercepts are for this, if they exist. If they don't exist, just tell me that.
How do you put the cube root in?
I was just about to mention that. So depending on your calculator type, you may be able to manipulate the index. If you can't, then I would recommend doing it this way. So use the caret symbol and then 1/3. So to the 1/3 power is the same as the third root. Okay, so you'll notice these don't occur at integers, and it's a little tricky to see where they are. You'll have to use some calculator tricks to give a good approximation. Let me show you what those calculator tricks are in case you didn't figure them out on your own. So we'll punch in negative, and then in parentheses, 8x squared minus 4. Then outside the parentheses, I'm going to put the power symbol, and then another open parentheses, 1/3. So that's equivalent to this expression. If I graph that, I see this real funky kind of shape. It's clearly got 2 x-intercepts and 1 y-intercept. But where do they occur? Well, you can't just look at the graph and tell in this case. You'll have to use a calculator trick. So if I hit second and trace, you'll notice me using this menu quite a bit. See, option 2 is 0. That will tell us where a 0 is if we pick our intervals carefully. So left bound, -1 appears to be to the left of that 0. And I don't know, negative like 0.2. And then here, guess is a little more important than it was before, because it's going to take your calculator a long time to find this if you don't guess fairly close to it. It's taking a pretty good amount of time here. So about -0.71, which is about the square root of 2 over 2. And then the second one, it's probably about positive 0.71. That looks symmetric to me. We'll just hit the trace and a 0.701. We'll just use it again. 2, left bound, that's good. Right bound, I'll go just past it. Yeah, 0.71 is a good approximation here. And then the y-intercept. The best way to find this is to just plug in x equals 0. So go to trace, hit 0, and I see it's about 1.59. Okay, any questions about that? That was a pretty tricky one to throw at you, but it did practice some good calculator skills. Okay, one more thing I want to do before we call it a day is solve a radical equation. So here's an example of a radical equation. These can get really algebraically messy. So you probably haven't seen quite this much algebra on a single problem before. Be prepared for it. So your first task is going to be isolate the radical. Your second task is going to be to raise to the power of the index. So let's isolate this radical. I'm going to begin by adding 3 to each side. Radical isolated. My index here is not listed, but it's understood to be what? What's the index to the square root? 2. Very good, 2. So I'm going to raise both sides to the second power. So 2x plus 3 squared equals the square root of 28x plus 29 squared. And here I'll use that shortcut. Remember that a plus b squared equals a squared plus 2ab plus b squared. So 2x quantity squared is 4x squared. That's the a squared part. And then 2 times a times b. So 2 times 2x is 4x times 3 is 12x. And then 3 squared is 9. So just using that shortcut to square that 2x plus 3. And then the square root and the square on the other side just cancel. Like so. Now here we have a quadratic to solve. So this is a whole different thing now. We're through with the radical equation part. We're now into a quadratic equation. So with a quadratic equation, we want to set equal to 0, and then use one of the 4 methods. And you'll remember they are graphing, factoring, and setting equal to 0 using the 0 product property, completing the square, and then also the quadratic formula. The quadratic formula is going to serve you pretty well when you have funky coefficients on x squared like this. So we'll probably use the quadratic formula, but let's solve it first and see. So subtract away 28x. We're trying to get to 0. And I need to subtract 29. So I have 4x squared, and then 12x minus 28x is negative 16x. And then 9 minus 29 is minus 20. And I can actually factor away. I can divide both sides by 4 here. And I'll have x squared minus 4x minus 5 equals 0. And this actually is going to be pretty easy to solve by factoring now. So I'm going to say x minus 5 and x plus 1 equals 0. And I'll set both of those equal to 0 using the 0 product property. So x equals 5 or x equals negative 1. But I'm not quite done yet. So once I find the solutions of a radical equation, I have to plug them back in to the original equation and see if they're actually true, because the potential for extraneous solutions exists. So as a final step, I look back up here and I take this original relationship, I'll copy it, and then I'm going to paste it. And I'm going to test it for both of these solutions. So I'm going to test it for x equals 5, and I'm going to test it for x equals negative 1. First of all, for x equals 5. So that's 2 times 5 plus 3 equals the square root of 28 times 5 plus 29. So 2 times 5 is 10 plus 3 is 13. 28 times 5. It's off the multiplication tables there. 140 plus 29 is 169. And so that's true. This one is a valid solution. With the other, x equals negative 1, 2 times negative 1 plus 3 has to equal 28 times negative 1 plus 29. So 2 times negative 1 is negative 2. Plus 3 is positive 1. 28 times negative 1 is negative 28. Plus 29 is 1. So this one also checks out. But don't let that lull you into a false sense of security that you don't really need to check these, because you do. Another neat way to check them, and as far as your ACT and other standardized tests go, this might be the most important trick I'll ever show you for the whole semester. This is probably going to bump your ACT score up the most, because it allows you to solve any equation, no matter what, even if you don't remember anything about the algebra, with your calculator. Here's how it works. I take the left side of the expression and I plug it into y1. So that's 2x plus 3. I take the right side of the equation and I plug that into y2. So that's the square root of 28x plus 29. Now again, I have to be able to manipulate my window to see where any intersections occur. We'll graph just on the standard window first. Okay, so there's something going on there. We need to zoom out. So let's change our y value, max y value, to 50. So guess where these two intersections are going to occur? Yeah. So any equation can be solved by your calculator with this method, even if you forgot the algebra, because I want to teach you all about logarithms. But when you go to take that ACT, you might be like, what the heck is this log crap? I forgot this. Well, you can still use this method to solve. So it bears committing to memory. Okay, so what I'd like for you guys to do for me now is page 92, numbers 4, 8, 16, 43, and 69. This is 5 problems. You can do this. So good luck. See you next time.